Yeah, we start with the general workflow. Everybody is familiar. Let me start. Let me go to pointer. Yeah, general workflow for the data processing. How to get from the raw recording to the events you need to extract and compare between different conditions. The first step is do the pre-processing to minimize the footprint of the recording, so make it manageable and the following processing faster enough. And then we typically do motion correction to stabilize the movie and then make it possible to detect cells or make it reliable to do the longitudinal registration. And then we have the delta F to F conversion just to detect the dynamic signal instead of the static signal. This step is required for one of the algorithm to detect cells, which is PCA-ICA. But for CMFE, since its way of handling noise is different, so all of those background needs to be preserved. So this step will be skipped. And then, as I said, PCA-ICA or CMFE are the two popular algorithms to detect cells. I recently heard CMFE can work better in certain situations if it's PCA-ICA give you some trouble. And after you detect cells, you can register those over days. So that way you can track the same cells and see how their active change at different paradigm at different days. And then you can use a simple amplitude or temporal profile to detect events. For some people, those are more relevant compared to the raw trace. So for the time series, we also have a time series. I just mentioned we have a longitudinal registration to overlay cell maps across days. But if you just have multiple sessions in one day, you want to do this for multiple reasons. For example, you want to give the mouse time to rest, so there will be a gap between sessions. For other cases, you might want to compare before the drop, so there we naturally introduce some gap. Yeah, and then you can concatenate those movies into one session. So which is we have a built-in function in the IDPS is a time series. Everybody's familiar. So that way you have the relative time or the absolute time preserved. So you can toggle between the two, the relative index or the absolute index. And after you export the data, you have the original timestamp. The purpose we do the pre-processing is really just make the file really manageable. For most people coming from electrophysiology background, those files are basically text files. It's pretty small, but for calcium imaging, you're talking about movies. And also if you're not using the downsampled movie, the raw movie is a huge file. It's like 1,000 by 800 pixels. It's a big frame of picture. And then if you overlay those recording with 30 minutes for 20 hertz, you're talking about tens of thousands of frames. Those easily can be over 100 gigabytes of data just for one recording. And then it's really slow if you do either PCA-ICA or CMFE, and it's really, really intolerable at some certain point. So with just simple downsampling, for example, if you downsample the movie by 4x, and for some GCAM, you can also use slower sampling and by 2x downsampling. And then you can reduce the file size by like 30 times. And then it's really becoming more realistic to do the following analysis. Those two, yeah.
Sorry, Jonah, I have a quick question. So
yeah,
it would be actually, it's, are you planning to mention the type of file that we can input in IDPS, such as, you know, the type of the formats, so IS6D or T files, for example?
Yeah, I think the default for the newer NVISTA and Vogue, we only have one format, right? I don't know about the old system. They have HD5, and then you have to use the decompressor to convert and then import back into the IDPS. Yeah, I think, do you have any troubles to import movie from our own system?
No, I mean, sometimes they just want to export as a TIFF for, some reasons and then re-import the file in IDPS. And in that
So
case,
how do you get
yeah.
the TIFF? You record it in TIFF format?
No. I mean, they record in ISXD, but then in IDPS, they basically export the file, like the processed data or the processed recording in TIFF.
Yeah, I think we have a built-in function to export the movie, all right? Or within IDPS, we have the export function. Yeah, I didn't, yeah, I forgot. Yeah, I think that's a great point to bring up. I think for some people, if they have their own pipeline to analyze, they don't want to analyze SXD or use the API. Yeah, they want just the the TIFF file. I
Yeah,
think
exactly.
within
And
IDPS, that's we can export at every stage, even before you do the pre-process, right? To the export.
yeah, also because we have some limitations with TIFF file. I think like one of the limitation is the time series. Now, if I remember, we can perform time series with TIFF file.
Yeah, for TIFF, I have haven't got a chance to play with the time series, but I think that when you export the CSV file, I noticed the timestamp is actually not consistent with this movie showing. So this is have no gap. But when you export to the CSV, I think the original absolute time was preserved. Maybe we can give the option. You can either keep the gap or maybe just keep everything continuous. And that way, each time series will be treated as a one big movie, and then it's probably easier to do following analysis, right? Is that something you feel because of the gap make something analysis more difficult?
Yeah, no, I mean, I don't. If I remember, there was like some issues with like doing time series with TIFF files. I don't know if it's still the case right now, but
yeah, there is, or there can be, because it doesn't save the timestamp information, the TIFF files. I think it's a good point. I don't know if we need to bring it up in every single demo because most people aren't doing that option, but might be something good to mention at some point that if you are going to export your files as TIFFs, you you may not be able to align the time series appropriately in the GUI. So you could just point it out, but I don't think we should spend a lot of time for every customer because most people won't do that and they might just get confused.
Yeah, I think that's a very interesting question. Yeah, I think Shay mentioned some format like OMIP TIFF, maybe another additional other format of TIFF, maybe preserve some of the metadata about the time series. Maybe in the future, next the IDPS, they maybe be able to do more to keep the time series within the TIFF, just using some other TIFF format.
So actually, the file formats will be important for legacy systems, which is quite a few out there.
Yeah, exactly.
And the problem with importing TIFFs is that they don't preserve the temporal information, or it's not imported. The metadata is not imported correctly. So that's why the time series gets messed up.
Yeah, and I think also we are limited. We have like a size restriction. So I think over, I think it's over 4 gigs. So we have like issues in opening TIFF files. But that was just like a question. Thanks. Sorry.
You think this may be something we can do with through API? We just rewrite the timestamp, might be able to solve the problem, since we do have the kind of cell set or movie write function. Basically, recreate modify the movie and save it as another file. Maybe we can import and then maybe do something, create a compatible ISXD file, and then later on you can do all the analysis you can do with the ISXD format.
Yeah, of course, that's something we could do with the API. But yeah, I mean, I agree that's not the priority for now for IDPS. So, but
yeah, I think that's probably a feature request. If a lot of people you have issues with the TIFF file, we can consider offer some API workaround just for them, so they can take advantage of the IDPS or API.
Patching.
Yeah, sure. Yeah, that's great. Since I only used for old system, I used to analyze TIFF files, but those were not in IDPS. I use our own pipeline in QuantSnap. So yeah, those timestamp is not so important, so we always know each event, each frame, how long is it. So that is, you can always recreate time series at any time point. Yeah. Yeah, so for doing the downsampling is pretty easy, straightforward in the pre-processed step. So which is the within this first is time series, the second is pre-process, and then on the top left, yeah, I'm probably just go very fast since everybody knows. Yeah, top is bar downsampling for spatial and temporal, and we also can crop the movie. And we should for the newer system at least, we could do this during the acquisition period. But if you forgot to do it, or for whatever reason, you can do the cropping here. And that the reason again just to minimize the file size, prevented wasted recording time or file size. So how much downsampling you can do temporarily, there's some signaling consideration each. So that's about the raw signal frequency and how fast you want to sample and to detect events. So it's also depending on the GChem you're using. For example, the GChem 6F will be a fast type, so each event will be faster. So we potentially capture the real dynamic of action, not action potential, but a certain events like a complex motion, which is happening at a millisecond scale level. And if you don't use the 6F, you will probably miss that. So, and then that is about 250 milliseconds for each event. But I think the rule of thumb is to have at least 5 points during that 250 milliseconds. So basically, you need a 50 millisecond sampling each duration, and then equalize to 20 frames per second. And for the GChem 6S, since it's slower, each event lasts 1 second, and then you can do either 5 points. That will be 5 frames per second, or 10 points, since we have some flexibility or room to increase the sampling here. This lifetime of the GChem was taken from the Chen paper in Douglas Kim group in 2013 Nature publication. They recently published a Nature method paper with a GChem 7, and I can only find the decay from 1 action potential for the GChem 7F. So you can see the GChem 7F is generally comparable to the 6M. So they don't have the very fast type. Basically, they just have the medium type, or for the slow type, this trace will be, the red trace will show the decay of the slow type, which is really the slowest of all, but it also have the highest signal to noise ratio. So if you want to trade off your detection speed with the signal to noise ratio sensitivity, and then you can choose the GChem 7S type.
Can you go back to that slide?
Yeah.
I mean, it's weird that their 2019 paper cites different numbers for 6S and 6F. Just a side note.
This is on the right. Yeah, this is about average of all their events. So may not be a single action potential. So yeah, so I can only find 1 action potential value from the 6-7F. Yeah, if we write to the group, maybe they can provide the 1 AP decay for every serotype. Yeah, but this is just a summary table for their in vivo data, which is not consistent since this is just 1 action potential data. To do spatial downsampling, we also have some consideration about how many pixels you want a cell to occupy. So basically, a cell size in physical size can be converted into pixel. So basically, you can, if you want the cell to be high resolution, you want to increase the pixel number, and correspondingly, the pixel size will be smaller. It's kind of like your iPhone. When the Retina display was out first, they just pack more pixels into the screen, and then each pixel will be smaller, and they achieve the highest resolution. And the highest resolution is determined by the sensor. So the sensor is about 900 micron by 650 micron, and then they can only pack 1,000 pixel, 1,200 pixel by 800 pixel. Then the highest resolution for a single pixel is about 0.2, 0.3 microns. That's about a single pixel size. And the reason sometimes you want to do downsampling, turn your retina display to a garbage display, is really just for the saving the file size to make it easier to do the further processing. And the point is really just to reduce the pixel number and then increase the pixel size. So each pixel would be larger. And from my experience for CMFE, to be really to finish each analysis within a reasonable amount of time, I typically use 4x downsampling, which is about 10 pixels each diameter. And then the following step is we typically have the spatial bandpassing filtering built in after pre-processing. This step is to remove some of the near-field signal background. So you can break down this raw movie into different spectrum. The low frequency spectrum across space, we have a slow luminous change, which is corresponding well to those near-field background. And then those highest frequency corresponding some noise. So basically the spatial bandpass filtering is to remove this low frequency noise from the near-field signal and then apply a Gaussian filter to those high frequency noise. And then what's the cutoff for the high frequency is you can determine in the program. So if you lower that value too much, you could blur the whole movie, the neural signal as well. So we will see that next. So as I mentioned, you have two cutoff values. One is for high cutoff. If you lower this value too much, the whole movie will look blurry. And the low cutoff will be how much background you want to preserve. Zero value meaning you don't do the bandpass filtering at all those near-field background will be preserved. Anyway, the default value will work pretty well. I don't see a need to change them, at least from my own experience. And then they have another parameter to check or uncheck is the retain mean. So this retain mean is to add back the baseline value during the spatial bandpass filtering, which is there's some background shift, and then there's you can add that just recalibrate the baseline if you check this retain mean function. This is just a maximum projection from those third F over F movie, and then you can see without retaining mean you have a higher contrast, but if you retain mean it become washed out. Yeah, so the next step after spatial bandpass filtering is motion correction. So this step is really important, and then we have a built-in motion correction algorithm. It could work pretty well, but you have to, in certain cases, you have to remove the lens border to make it more robust. So you can have a RI function just to draw around the lens border to make sure the algorithm applies to the tissue, but not the lens border, since lens border typically is more static, and if you include them, it probably will interfere with your motion correction efforts. We have a flow chart, a decision, so which frame you want to use as a reference frame for motion correction. Typically, we have a average projection, and the mean average will be used as a reference frame. And then if you have a lot of motion, the mean frame might not work well. So we can use any single frame. We can give an index based on what you see in the IDPS. Just find the one with pretty good stability and use that as a reference. And if that still doesn't work, we have another parameter to tune is called global registration weight. So a default value is 1. That is just limit the motion correction to the reference frame mode. And if you change the value to another below 1, then we can use the previous frame as a reference to correct the drifting. So basically you can mix the two mode, either a reference correction or frame by frame correction. And as I said, the RIs it's typically important when you have a lot of motion within lens, and we can usually use whenever we see that. So yeah, it may not help in every case, since in a certain brain area close to the ventricle zone, if we have built-in motion, and we have to think about how to improve that at the surgery step instead of the post-processing. Yeah, we'll talk about the two algorithms to do the data analysis. The PCI-SCA is one of the old one. Yeah, we talk about some of the conceptual background behind PCI-SCA very briefly, since you have heard multiple times from the science team. From frame number requirement, I think for the good movies, distinct activity, I think 5,000 is enough. But if you have a very low signal to noise ratio, you might want to increase that to maybe 20K for the difficult if the PCI-SCA result is not optimal. So the reason why we want an automatic algorithm instead of manual RI is really just the way how robust and time saving compared to the manual RI. And also when two cells are close to each other, for example, we have a diagram, the blue and the red. And if you just use the spatial information to separate the cells, you will fail. So the maximum projection will treat them as a single cell. If you want to use their temporal profile, for example, these blue represent the activity at a time series, and they have overlapping firing, but they also have some differences at different time points. If you go into the movie to try and pick up when they could be different, those would really be time consuming. So the automatic method from PCI-SCA will solve these issues. So this method, PCI-SCA algorithm, was published a while ago by McConnell, and the idea is to correlate the movie frame from your raw recording to the cell activity in the cell print. So if we have the cell map and their activity, it is pretty easy, for example, for simulation purpose, to construct the raw movie. And for example, at the first frame will be only contributed by the active cells or their dendrites, and then all those inactive cells, even though they occupy the space, and then they don't contribute to the movie frame. So that's really easy if you do have knowledge of the footprint or activity through the construction. But if you want to do the reverse engineering, it will be more difficult, but there is possible to using some mathematical tools. This is illustrated on the left. So each cell will be treated as a matrix of pixels. So this cell S1 will occupy 4 pixels, one meaning they occupy the space, and the other cell occupy the other 4 pixels, and they have some overlap. But their activity could also be different. So at this first frame, this first cell is active, so they will contribute to the luminance level at the first raw movie frame. And then at different time point, their contribution from different cell will be different depending on the activity level. The 0, 1 will be simplified, so 1 will be active, 0 being inactive. So basically with this sum of the spatial footprint and the activity, we can kind of do the estimation to just reconstruct the raw movie. But actually we're doing the opposite, just decompose the footprint and traces from the raw movies. Yeah, the PCA component is a little bit different from the ICA. So PCA is more related to the noise reduction. So for example, if I have 2 cells, noise is in another, it's surrounding them. If you have their luminance plotted, and PCA is trying to distribute them into different dimensions, and the noise can be simplified in this case in 3 dimensions. The noise can be thrown out since they occupy the 3rd dimension in Z. And after throwing out the 3rd dimension, we preserve most of the signal, so in 2D in this case. And then the ICA will be decorrelate the signal and separate them out into their both the spatial footprints and their activity level. So those would be simultaneous output from the IC output. It's important to have some inspection, since in this case, you also can detect a dendritic signal, and sometimes it could be false positive. So we have built-in cell inspection function. You can reassign the category of the neurons either as good one or bad one, or undecided. You can check back later. And the cell footprint and the traces you can will be output from the ICA, and you can export those as well. Since the footprint from the raw output will be still contain some of the background, and you can do some further thresholding and to binarize to get the cell map, more distinct cell map. Just to address some of the cons of the PCA ICA, we do have some of the noise reduction from the PCA component step, but it's not specific targeting to the noise, so it may not be accurate or adequate. And then also assume some of the independence during the ICA step. And then if signals are kind of correlated, highly correlated, then it might introduce some decorrelation artifact. So I will talk about some event detection. So we are using both amplitude-based and also temporal profile-based thresholding values. The temporal profile is based on their one action potential decay time, a little bit conversion to the 37% tau, typical tau. And this is a built-in 200 millisecond is applied to the 6F. If you want to use other GCAM, and then you can do the similar calculation to match the GCAM the customer is using. Just to make sure the customer aware of this feature, and they can apply the right temporal filter to their recording to have the optimal event detection. Yeah, one common asked question is about the scale of the traces output. The Y scale from the PCA-ICA, I think it's complicated. From the spatial unmixed cell traces, it's not exactly Z-score. It's kind of related to the input movie, but I think it's recommended to convert into Z-score. It's pretty easy mathematically, just to subtract the mean and divide it by the standard deviation. I think CMFE can also do the same thing, since the trace might be deconvolved like a spike rate, and then it may not be accurate, or maybe some people just don't like the spike rate, and they can use the similar conversion to the Z-score. The manual RI is relatively straightforward related to the input movie. So if you're using the DF over F, it will be relative fluorescence change. And we have the apply contour function. We are basically doing the same thing, apply using the cell map to extract the delta F over F traces. And then the scale would be the relative fluorescence change instead of the arbitrary unit from the PCA-ICA in some cases. The launch,
I guess it's fair to say that if it's applied contours, it's kind of like a percentage, right?
Yeah, I think it's just applied, basically treat those as automatic RI, use those cell map as a kind of RI, and then take out all this delta F over F traces from the movie.
Yeah, no, but like if you apply if you do the apply contours to the delta F movie, like I guess the one way to express that scale would be a percentage, because
percentage is the noise ratio, how much percentage change you see, 5% or 10%. Yeah, this is relatively easy to understand. Sometimes people will get confused about the PCA-ICA unit, since it's not really Z-score. It's kind of related, but you probably want to do some conversion within Python or MATLAB. It's mathematically it's not complicated, but just one step processing. Maybe Shay, then they can work on additional processing, to convert that to another scale.
Ching, Jonah, quick question. So that is the case if we use the default PCA-ICA that I think is the spatial PCA-ICA. But if we run the temporal PCA-ICA, then the Y value is the standard deviation.
Yeah, I think if you do the temporal or maybe mixed type, it will be probably Z-score, but I think it doesn't hurt, right? If you do another conversion again, it should probably be the same. Yeah, I think the simple case just do this step building, yeah, with another command or maybe in API, and you just do another further one-step processing. Yeah, make it a consistent. Everybody. It can also be applied to CMFE, right? Since mathematics is the same thing. Take whatever y and then just calculate that.
Okay.
Yeah, the longitude registration, yeah, I won't spend too much time. It's just, I think one thing I noticed is that the algorithm is relatively slow, especially when you have multiple days of recording. That's what I noticed. I don't know if anybody have the experience from the longitude registration. It can work, but it's kind of, yeah, it's not the fastest way. I don't know why, if it is a calculation is time consuming. Yeah. Yeah, but basically it will register all those session independent cells, use those as anchors, and then all those session dependent cells will be anchored into this one combined cell map, and then that way you can notice how many cells active in more than one session, or how many cells are active across all the sessions. Yeah, so I will list some of the reference, so those would be useful for the customer. The menu is definitely more detailed than this short introduction. And some of the background for the motion correction PCICA and CMFE, everybody knows is it's published this CMFE is just published a few years ago. We have a webinar also listed here. It's a pretty good one from Sabrina and Arden. Yeah, I also list some CMF intro in the next few slides, just to refresh everybody, and then yeah, make some basic explanation. CMFE compared to the PCICA, it's really have a unique feature to estimate the noise. It's built in their mathematical calculation. That's a distinct noise component. So the noise is calculated around the cells. That way, after estimating the noise, you will have a cleaner neural background. So they will be smoother, and then the deconvolution, spike deconvolution will be a lot more accurate. So you will want to turn the action events into number of action potentials. So the end result will be separation of neural signal plus some fluctuating background from the noise, and maybe drifting over baseline. And then they have a distinct several steps. First, we initialize the same spatial and activity footprint. And then this is called seed initialization. And we use this seed to do the noise estimation, and then do iteration and going back and forth between noise estimation and cell refining in their spatial and activity map. So this is a kind of time consuming, but they have offer more parameters to tune and make the cell detection much more robust and accurate. One of the first parameter is really straightforward. It's just the cell size. If you have to just match the cell size, the G size, to the number of pixels you see from the movie. And if you do the 4x downsampling, if you see 10x pixels, and just use 10 as the G size. And G-sig is just the G size related filter to make the cells look more distinct. And those generally you can modify the two in parallel. And the other two are very useful is the minimum correlation and the minimum P&R ratio. So the correlation map will be determined by the value you set with this mean correlation. So what it does is really how many pixels you want to include in the seed initiating. The higher the value, the more conservative it is. And the P&R value is very similar. If you set too high peak to noise ratio, it will have fewer seeds to start. And combining both P&R and correlation image, if you have a seed image, those will be used as a seed initialization. And so, yeah, so those two values, you can start with relatively high to have fewer detection. And then if you want to include more cells, and then you can lower either one or both and make it a corresponding better to your data set. Yeah, so I think this CMFE is really a great alternative to the PCICA, since with these just 3 parameters, you have a lot of more accurate map corresponding well to the human impression of where cells are located. Yeah, just talking about some of the pros and cons of the CMFE. It addresses some of the pain points of the PCICA, like the noise estimation is more explicit, and then also have no such independence artifact if the cells are really highly correlated, and also have at least a few more parameters. In the regional common package have more parameters, but in our API, we make it more practical, open some of the most often used ones, like G size, a mean correlation, and a mean PNR. I think with the offline CMFE is traditionally more computationally intensive, but I think there's some development with some online CMFE. Maybe Shay, they were considering implementing some of those in the future IDPS. That potentially be a lot faster, hopefully. And then because there's so many parameters, maybe tune some will achieve the same result, and then it's hard to do the quality control to make sure everybody is consistent. But yeah, those are kind of minor. Yeah. Yeah, just the last slide to just to ask customers to contact FSC if they have any issues during the data analysis. For example, the motion correction is inherent to their surgery or the brain area, and then we have to help them do some be creative, use some wide assembly approach. And for CMFE and PCICA, you might get a lot of questions, I believe. Yeah. And also, yeah, to optimize event detection, yeah, I think you will probably get a question for that as well. Yeah, that's all I have.